So we are in the home stretch. I know we've had a busy day today. So we'll just end with a few comments about the direction some of our new work is heading. And in particular, you've heard some people speak about the xSDK, or Extreme Scale Software Development Kit, and SPAC. So I'll tell you a little bit about what we're all working on now on those fronts. So first, a bit of history. A team called the Ideas Software Productivity Project began working in the fall of 2014 to look at issues that were inhibiting the combined use of software developed by different groups. And this is a collaboration among a variety of labs, as well as the Colorado School of Mines. And we're really motivated by the needs of our partners who are working on subsurface modeling. So this is a partnership between the Advanced Scientific Computing Research Division in Office of Science, as well as basic energy research. And later this week on Wednesday, a team from our project, including Mike Haru, Anshu Dubey, Alicia Klinvex, will be speaking about some of our work in the Ideas Project that focuses on methodologies or approaches for helping to develop software that is more productively and more sustainably. So I'm not going to talk about that here, but I just want to emphasize that the work that we're doing in the xSDK project began as one of the activities within this Ideas Software Productivity Project. And really, this diagram here shows the motivation for what we need to deal with in some of the next generation applications. As Lori discussed this morning, multiphysics problems oftentimes require the combined use of different packages that are developed by different groups. And this diagram here shows that the next generation modeling and subsurface flow that our partners want to do requires using different subsurface applications, as shown here, Amanzi, CrunchFlow, ParFlow, pFlowtran, Alchemia, CLM. And those in turn have already been built using many of the libraries that we've talked about here today. So they're built on top of Hyper, SuperLU, PETSI, Trilinos, Sundials, and Chombo. And so when we began this partnership, we had real challenges because we couldn't compile together into a single executable all of this software because there were all sorts of conflicts. And so we wanted to be able to work towards more sophisticated numerical algorithms in multiphysics, but first we had to solve some of our foundational problems just in incompatibilities among different packages. This slide shows our vision for what we're working toward in the xSDK project, and that is we want to work as a broad community engaging whoever's interested, so that would be all of you, towards an ecosystem where we can more easily share software and leverage the capabilities that other people have developed, and also share the things that we have developed so that they can be used more readily by other people who have needs for them. And this diagram shows at the bottom level what we're working on in the xSDK, or Extreme Scale Scientific Software Development Kit, where we are looking to build a suite of domain components for various kinds of scientific software capabilities. In particular, we're working on subsurface flow components now, but you could imagine components in all sorts of areas, in physics, chemistry, biology, et cetera. Our particular area of focus as numerical package developers is in libraries and software for numerical capabilities, but we're also working with the rest of our team on some other issues in terms of frameworks and best practices and whatnot. So this is what's motivating our work. And really, we're trying to increase the functionality and the quality and the ability to combine together different capabilities. And the impact of our work, even thus far in the limited time we've been working on this, is that we believe we've strongly improved the quality of the code of all of our libraries that you've heard us talk about today. And we've also built a strong foundation for looking at deeper levels of package interoperability that we know we need to do as we are moving toward exascale. So we are beginning to now be able to combine our tools together, but we have a lot more work to do. So information about this project is available on the website. This cartoon shows our initial release of the xSDK in April of 2017, where we released a version that included the combined release of 4 numerical packages, Hyper, PETSI, SuperLU, and Trilinos, as well as 2 application components, Alchemia and pFlowtran, that were used in our subsurface models. And we are working towards distribution of all the components using the SPAC tool for package installation. So in this release, we were able to overcome our problems that we had at the beginning of this project by developing community policies whereby we work together so that our software could be used in a combined way. And I'll talk more about that in a minute. First, a word about SPAC. You've heard a number of people discuss that today. This is a package manager for high-performance computing software developed by Todd Gamblin and his collaborators at Livermore. And as you can see from the diagram at the bottom, over time, the SPAC community has been growing tremendously. It's a very strong community, which is getting many, many people involved in contributing their packages so that there's opportunities for them to be built together and used together. And so from the perspective of the xSDK, in our initial release that we did in April, we used SPAC so that through this package manager, the independently developed software that I mentioned was able to be installed in a combined way together. So that's been a work in progress. There's certainly a lot that we're continuing to need to do to fully test this on a variety of architectures and to make sure that the infrastructure is up to the task for what we really need to do. But we're making very strong progress, and we're excited about the direction that we're headed here. So next I'll mention a few words about the approach that we've taken in order to enable compatibility among our packages, which are all developed separately and independently. So we recognize that as software developers, package developers, we all really do have different needs and motivations and constraints. We have different sources of funding, and we have a variety of different ways in which we like to collaborate in different aspects of our work that we like to emphasize. So as an initial community of package developers, we agreed on a set of community policies that we all agreed to support in our packages in order to help them be compatible. And we're not going to go through these in detail today, but at your leisure, we encourage you to go take a look at the website and look at our draft policies and think about whether they might make sense for the software that you're writing. And we welcome feedback. The website enables you to comment on our current draft policies. They're available in Google Docs, which are world commentable, so you can go in there and write your comments. I'll just mention, for example, one of the policies that is important is using a communicator for MPI that's provided to the library by whatever's using it. So as package developers, we do not expect that we own all of MPI ComWorld, for example, but we need to work within the context of whatever communicator is given to us. So that's policy number 3, and a simple one to understand. Some of the other policies here that overcame some of our challenges that we initially faced had to do with approaches for building the software and also overcoming namespace challenges. So we'll be glad to talk with you in more detail this evening if you would like to talk about this. So within the context of the exascale computing project, we're now building on this initial foundation and working to extend based on the needs of the wide variety of applications that are part of the ECP application suite. So there are many different application needs there, and these rely not only on the initial libraries that I mentioned, but also on sundials, Jumbo, Alexa, which includes a variety of packages, including AMP, DTK, and Tasmanian, as well as the dense linear algebra package that Jack Dungera mentioned today. So as part of this project, we are all working to continue to expand the community packages that are part of this collaborative effort. And we're also working to figure out how we might need to revise and extend the policies based on what's needed for ECP. So these policies are very much alive and living and growing and adapting. So we encourage you to provide feedback. And we welcome you to also consider contributing packages to the xSDK. We're group that's based on policies. So if your package follows the policies, you're welcome to be part of the xSDK. It's as simple as that. And we have 2 different categories of memberships. You can either be just compatible with the policies, or you could, if you also use another package in the SDK, or can be used by another package in the xSDK, and you test that interface regularly, then you can also be a member package. So we believe that this approach is helping us to have better quality software, to work as a broad community towards an ecosystem of interoperable software, and thus is helping us to work toward the vision of predictive science, optimization, and design that Lori discussed in the beginning of today's presentation. And importantly for us in ECP, this is really providing a strong foundation for us to delve in and to work on deeper levels of package interoperability that we know are needed as we move forward. So that's all for me for today. If you have any questions, I'd be glad to address a few of them now. Otherwise, we can talk more informally tonight when we're back for hands-on. I know we have a dinner session now, and then we'll have our evening hands-on session later. So thank you. Okay. One question? Yes.
Yeah. I really like the the community effort and this thing. But why do you develop SPAC? Why don't you use like easy build or something like that?
The question is, why are we using SPAC as opposed to
Easy build or
well, SPAC is
similar?
specifically designed to help us deal with the high-performance computing environments that we're working with. And so the intent is to try to leverage those capabilities to be flexible and adapt to what we need in that context. So there's certainly other types of distribution that we're considering in terms of containers and whatnot. So over the long term, there's a mix of a variety of capabilities that we know are needed, and this is a starting foundation.
Just another comment on that is SPAC sort of solves the combinatorial installation problem in that, oh, you need this with optimization A and that with, compiler B and this with, it allows you to manage that complexity quite well. And it's working from sources. It's not like any of those other systems are working from binaries. I know Easy Build works from sources too.
SPAC, what is the learning curve like compared to something like CMake? Or I'm just wondering how difficult to get started with SPAC.
It's very easy to get started with it. You git clone it. You can try it today on your Mac. Git clone SPAC repo, and then try like SPAC install HDF5, and that'll install HDF5 and all the things that HDF5.
Well, how about for packaging something that you want?
Oh, you have to write a package for it?
Yeah.
There's definitely a learning curve to get into that for sure. Because you have to be aware of the way SPAC thinks about installing software. Okay. Yeah.
But there is a great deal of very useful information on the SPAC website, and including introductory material and tutorials. So I encourage you to take a look.